Hello there, amazing students and all the lovers of chemistry out there. I'm so excited to be here with you today on this special episode. My name is David, and as you know, all I do here is to take the mystery out of chemistry so chemi can make history. All right, so today we want to look at something quite interesting, how to name organic compounds. This is going to be an easy step-by-step guide to IUPAC naming for beginners. All right, so if you're here, you're yet to learn about how organic compounds are named, this video has been made just for you. Okay, and today we're going to be looking at just how to name alkanes. So let's get into what we have for this video. All right, so let's look at the importance of naming organic compounds. What is it all about? Now, there are millions of organic compounds existing. So this makes a clear and systematic naming system important or essential, because without proper naming, there would be confusion in identifying substances. You just imagine all over the world, there were no names with which we identify people, or even in your family, your dad, your mom, brother, sister, auntie, uncle do not have, all of them do not have names, and then a stranger comes to the house visiting and is trying to call somebody and he's saying, "Hey, you," and then everybody turns to look and they say, "No, no, no, I'm not talking to you, I'm talking to the other person." It will be all confusing. It will be all confusing. So, without proper naming, there will be confusion in identifying substances. Imagine trying to communicate a chemical formula without a structured name. So, therefore, scientists need a universal way to describe compounds accurately. So that brings us to the overview of what I call the IUPAC naming system. There is a system for naming organic compounds, and that's the IUPAC naming system. So to avoid confusion, chemists follow the International Union of Pure and Applied Chemistry, that's the IUPAC system. This standardized method ensures that each organic compound has a unique and globally recognized name. So there is a system that we follow, a pattern that we follow before any compound, particularly organic compounds, can be named. This system ensures that no other compound, no other organic molecule carries the name of another compound so that there will not be confusion. So the IUPAC system is based on clear rules. Rules such as identifying the longest carbon chain, numbering the atoms correctly, and recognizing functional groups. Mastering these rules allows us to name and to understand any organic compound effectively. So now let's see the basics of organic compound structure. You see, recently in one of my previous videos, I talked about the introduction to organic chemistry. And one of the things we stated is that organic chemistry is the study of compounds that are built around a carbon backbone, because every organic compound contains the element carbon. In the same way, here I'm saying organic compounds are built around a carbon backbone, a carbon framework, a carbon structure, which serves as the foundation. So now, attached to this backbone are something we call functional groups. Now, functional groups are specific atoms or groups of atoms that determine the compound's chemical properties and reactivity. For example, look at some functional groups that we have here. We have hydroxyl. Hydroxyl is also called the alcohol functional groups. Now, there is a way alcohols behave that is unique to them. For instance, alcohols readily dissolve in water, or they easily dissolve in water, and that is because of the hydrogen bonding that is present in their functional group. So functional groups are those things, those molecules or those group of atoms that make an organic compound or any compound to behave in a particular way. Alright, so having talked about that, now we are coming to the part where we'll be naming alkanes, alkenes, and alkynes. But let's talk about them briefly. What are they? First of all, organic molecules can be classified based on the types of bonds between the carbon atoms. First, we have alkanes. Alkanes are single bonded hydrocarbons that are saturated. For example, you can see it's been pointed at the bottom left corner of your screen. That's a good example of an alkane. If you check, you will see that only single bonds are existing in the structure. So alkanes are hydrocarbons that are saturated, that have only single bonds throughout their entire structure. The next one is alkenes. Alkenes are hydrocarbons that are unsaturated because they contain double bonds. That double bonds does not allow for the complete spread of bonds around the carbon framework. As you can see here, the second example, heptene, which is at the middle, you can see there is a double bond at the first carbon, which doesn't allow the bond to spread around it. So that's why it is called unsaturated. The third example, alkynes. Alkynes are unsaturated hydrocarbons that have triple bonds in their carbon structure or in their structure, and they are highly reactive. All right, so these bonds impact the compound's physical and chemical properties, such as boiling points and reactivity. So now we've come to the main and the interesting part of what we have for today. There are certain rules for naming organic compounds. The naming process follows a structured approach to ensure that every compound has a unique and globally recognized name. Here are the basic rules. Number one, to name an alkane or an organic compound, because today we're going to be focusing on alkanes only so we can take it step by step. Identify the longest continuous carbon chain. That longest continuous carbon chain happens to be your parent chain. Then number two, number the carbon atoms in the chain to give priority to functional groups and substituents if they are present. Now, all these rules that I'm mentioning, we're going to be going over them one by one for every example we'll be dealing with. So I want you to relax, okay? The third one is name and position the substituents. The substituents are also the branches or side groups in the structure based on their location on the parent chain. And then number four, use prefixes, that is e.g. methyl, ethyl for substituents or side groups, and then use the prefixes. ANE is for ane, ENE. ENE is not ene. ENE is not ene. Benue people, please take notes. I know some people are saying ene now. ENE is not ene. ENE is in, okay? ENE is in, all right? And then YNE is ein. All right, so in, and ein for bond types. We'll be saying how to do that. And then the fifth rule is if multiple substituents exist, arrange them in alphabetical order and use numbers to indicate their position. Now, let's see how to identify the parent chain. The parent chain is the longest continuous carbon chain in a molecule. Take note of those two words, longest and continuous. It forms the base name of the compound. You begin by counting the number of carbon atoms to identify the prefix. Now, if it is one carbon in the parent chain, it is called meth. If it is two, it is called eth. If it is three, it is called pro, four, but, 5 pence, 6 hex, and so on and so forth. Now look at this. For straight chain alkanes, the number of carbons determines the name. For branched compounds, the longest chain may not always be in a straight line. We'll be saying that in an example we'll be treating shortly. Alright, so if there are multiple chains of the same length, choose the one with the most substituents that are attached. Now, example 1. Look at this structure. We have 4 carbon atoms and it is saturated. Now remember, we're going to be dealing with just alkanes in this video, okay, so relax. Now, first things first, the rule says identify the longest chain. Now this one is straightforward. As you can see, there are only 4 carbon atoms and they are straight in the longest chain. 4 carbon atoms stands for BUT. The longest chain here is 4 carbon atoms, stands for BUT, which is boot. And then adding the suffix for alkanes, ane, gives us but plus ane, which gives us butane. So that's the name of the first compound, butane. The same thing applies to the second example. You can see the longest continuous carbon chain here consists of 6 carbon atoms. And then that gives us the prefix hex, hex. And then adding the suffix for alkanes, ane, that gives us hexane. So the key takeaway in this point is that the parent chain is the longest straight sequence of carbon atoms. So having dealt with that, let's get into a more complex example. Example number 3. Here is this branched alkane that we want to name right now. Step 1 says identify the longest continuous carbon chain. Now looking at this, there are 2 ways in which we can identify the longest continuous carbon chain. Actually, there are more than two ways that we can do that. But if we want to identify it in a correct way, then there are two correct ways, and I'll be showing you that. Now, down below, you can see there is a first step, or there is a first style with which I have named it. I started from the left hand side and then I counted 5 carbon atoms. And then there is another way in which I did it. I started from the upper side and then I came down and moved to the right and I still counted 5 carbon atoms. In that case, the longest chain here consists of 5 carbon atoms, which gives us the prefix pent. Remember, pent stands for 5 carbon atoms. And I'll be showing us the next step to take. Now, step number 2 says number the carbon atoms in the chain to give priority to functional groups and substituents. When they say give priority to functional groups and substituents, it means if there is a substituent present, you are to assign the lowest number that is possible to that substituent. Now look at this. If you check the first drawing that has a green mark or a green tick on it, you will see a circled element, a circled CH3. It is showing you that for that pattern of counting, anything that is not part of the parent chain becomes a branch or a substituent or a side group. I'll repeat that. When you count your parent chain, if any carbon atom is not part of that parent chain, then that carbon atom becomes a substituent. So now look at this. For the first style of counting, you can see I have counted my 5 carbon atoms. There is a carbon atom or a CH3 group there circled in red that is not part of the parent chain. That automatically becomes a substituent. The same thing goes for the second style of counting. You can see on both sides, the first style of counting and the second style of counting, I have my substituent to be attached to carbon number 2. So that style of counting actually gave priority to my substituent. And you can see the last two styles of counting does not give priority to my substituent because they will be attached to carbon number 4. So you can see it's not just about counting the parent chain or the longest continuous chain, it's about counting it in the correct way. So there is a note at the bottom that says the first two ways of counting gives number 2 to the methyl branch, while the last two ways gives number 4. So that is why the first two ways are correct. So the next thing now is step number 3. Name and position the substituents based on their location on the parent chain. So now use your prefixes methyl and ethyl for side groups, and then use the suffix ane, ene, and yne for bond types. Now, what type of substituent do we have? We have CH3, and CH3 is called methyl. You can see the note below that says the substituent or branch here is CH3, which is called methyl, and it is placed on carbon number 2. If you check well, you will see that carbon number 2 is the point at which methyl is attached. So to name that, we simply say 2 dash methyl. That is how you name substituents. You put the number first and then you place a dash between that number and the name to name it accurately. I hope you are following. By the way, if this video is educating you appropriately, please go ahead, subscribe to this channel. That is the way that we can reach more people. Like this video and share to your friends who may be finding subjects or concepts in chemistry a bit difficult. I'm here to help. All right, now next step. If multiple substituents exist, arrange them in alphabetical order and use numbers to indicate their positions. In this case now, we have just one substituent, which is methyl, and we have named it. So since we have successfully named it, all we need to do now is to bring all the factors together. We've named the substituent 2-methyl. We've numbered the carbon atoms or the longest continuous carbon atom chain, which is the parent chain, which is 5 carbon atoms, which gives us pent. So 2-methyl plus pent, and it is an alkane. So we add this suffix ane, 2-methyl plus pent plus ane, it gives us 2-methyl pentane. 2-methyl pentane. I hope this example is clear. Let's look at another example before we call it a day. Look at this structure now, and we have been asked to name it. Step number 1, identify the longest continuous carbon chain or the parent chain. Now look at this. There are 4 styles that I have given on how you can find the longest continuous parent chain. You can start from the left. If we start from the left, how many are we going to count? We are going to count 5. And remember, any carbon atom that is not part of the parent chain, automatically it becomes a substituent or a branch. So now let's keep that at the back of our minds. For the first style of counting, you can see after counting, I have two substituents. I have a substituent on carbon number 2 and I have a substituent on carbon number 3. Substituent on carbon number 2 and a substituent on carbon number 3. Look at the second style of counting. I started from the left as well, but when I got to the third carbon atom, I went up. Now look at this. 1, 2, 3, 4, 5. So therefore, on the second style of counting, you can see I have a substituent on carbon number 2 and on carbon number 3 as well. The same thing goes for the third style and the fourth style. I started from the bottom in the third style, and then when I got to carbon number 2, I went right. And then on the fourth style, I started from the bottom, and then when I got to carbon number 3, I went up and then sideways. Now, if you check for all these four styles of counting, you will notice something, that there is a methyl substituent on carbon number 2, and then there is a substituent on carbon number 3. Now look at this. Note that we counted the longest continuous carbon chain in such a way that the branches or the substituent had the lowest number possible. Now there is no other way that you can count that the substituents will have a number that is lower than 2 and 3. So even if you are counting the longest chain and the substituents are having a number that there is another way you can count that will give them a lower number, then that counting is wrong. I'll take that again. Look at how we have counted in all these four styles. I made these four styles available to show you that when you are counting, you are not just to be, it's possible that you can decide not to be limited to just one way. All we need you to do is make sure you get the correct number of carbon atoms in the parent chain and then assign the correct number to the substituents present. So now if you observe very well, there are 4 possible correct ways to count the longest continuous carbon chain. Doing this gives us 5 carbon atoms, which is pent, and all the parts that were circled in red shows the branches or substituents for each counting pattern. Step number 2, number the carbon atoms in the chain to give priority to functional groups and substituents, each if present. Now look at this. All these numbering patterns are okay because they place methyl, which is CH3, at carbon number 2 and ethyl, which is C2H5, at carbon number 3. Now if you check all my styles of counting, number 1, number 2, number 3, and number 4, all those parts that have been circled in red are not part of the parent chain for each style of counting. And remember, if a carbon atom is not part of a parent chain, automatically it becomes a substituent or a branch. So you can see each branch in each style of counting, methyl is part of it, ethyl is also part of it. And methyl carries number 2, ethyl carries number 3, which are the lowest possible numbers that can be assigned to it. Now, step number 3, name and position substituents, which are also called side group based on their location on the parent chain. Now, methyl is on carbon number 2 and ethyl is on carbon number 3. Look at this. That gives us 2-methyl and 3-ethyl. That's how we named it. 2-methyl and then 3-ethyl. We're coming to the part where we'll bring everything together. Now look at this. If multiple substituents exist, arrange them in alphabetical order and use numbers to indicate their positions. In this case, we have two substituents, methyl and ethyl. Now, since ethyl comes first in alphabetical order, because the first letter in ethyl is letter E, the first letter in methyl is letter M, and E comes before M. So therefore, what we are going to do now is to say 3-ethyl and then 2-methyl. I hope you understand. The reason why we're putting ethyl before methyl is because E comes before letter M. So when we want to name everything, we'll make sure that ethyl comes first before methyl because we arrange them in alphabetical order. Now look at bringing everything together. First of all, the longest chain is 5 carbons, pentane. An ethyl group is on carbon number 3, which gives us 3 ethyl. A methyl group is on carbon number 2, which gives us 2 methyl. Since we have 2 branches, to write their names, we have to arrange them in alphabetical order. We have ethyl and methyl. Ethyl will have to come first because its first letter, the letter E, comes before M. So the final name therefore becomes 3-ethyl 2-methyl pentane. 3-ethyl 2-methyl pentane. So the key takeaway for this example is even if a branch makes the molecule look zigzagged, find the longest path. So that's it for today's video. But before we go, I'll give you one more bonus examples. In a case where 2 chains have the same length, what do you do? Then the one with more substituents win. Now look at this example. How do we identify the name of this structure? Now, for this structure, you can see there are 2 possible ways of counting. For the first style of counting, I started from the left to the right. For the second style of counting, I started from the top and then came down towards the right. For each style of counting, you can see if any carbon atom there that was not part of the parent chain became a branch or a substituent. Now you can see I've counted in 2 ways. For the first way that I've counted, there is a methyl substituent on carbon number 2 and a methyl substituent on carbon number 3. The same thing goes for the second style of counting, a methyl substituent on carbon number 2 and a methyl substituent on carbon number 3. So now, the longest chain contains 4 carbon atoms, which gives us but, which is but. Now, in step 2 says identify the branches of the substituents. You can see we have 2 branches, which are both methyl on carbon number 2 and carbon number 3. So we identify them by saying 2,3-dimethyl. When a substituent appears more than once, if it appears twice, we say di. If it appears 3 times, we say tri. In this case, it appears 2 times, so we say dimethyl. So bringing everything together, it gives us 2,3-dimethyl butane. I hope it is clear. I hope it is clear. So at this point now, I have some exercises that I want you to attempt. I have 5 exercises for you. Go ahead, attempt them, and then let me know their names in the comment section below. And if there's any question you have, I'll be so excited to answer them for you. So that's it for this video, guys. I've shown you how to name alkanes in this video. If there's any other topic or concept you want me to deal with for you, please let me know in the comment section below and I'll be more than happy to do justice to that for you. Till I come your way next time, I'm David, and remember, all I do is take out the mystery from chemistry so chemi can make history. Thank you very much and see you next time.